Hello Year 9s, here's my hand. So we're going to revise chapter 3 today in the textbook, and that's all about angles. So basic things that you need to remember for all angles type questions. These things might come up. So total angles, as you go around a circle, they total 360 degrees. In a circle or around a point, on a straight line. So here's a straight line, those two there. Total angles are 180 degrees on a line. And then the other one that you need to remember is that opposite angles, where two lines meet, are always equal. So opposite angles are equal. So that one's equal to that one. Similarly, if I just put it in purple, perhaps that one is equal to that one. Okay, so those things will hold all the time. Other things that you need to remember, so I'll just sort of make notes on this page, and we'll have a page of things that you need to know. Parallel lines. Now remember, parallel lines are always the same distance apart, and they are indicated on a diagram by the little arrow. Okay, and if you find yourself doing a sketch and, like me, your lines aren't beautifully in line with each other, then actually those little arrows say to the world that those lines are supposed to be parallel. So when you've got a line going across them, they call that a transversal sometimes. It makes angles with the parallel lines. And so you've got things going on, like you've got two lines meeting here, so we know that there's 360 degrees around the point. You know that you've got 180 degrees on a line, etc. But we've also got some special angles that relate to parallel lines. And the first one we're going to look at, that one and that one, would be examples of them, but so would that one and that one. And they are called alternate angles. So alternate angles are equal. Now, when you're answering a question, you must use the word alternate, because that's what gets you the marks in a question. So please make sure you use exactly that phrase, okay? Similarly, you've got angles that are in the same position relative to the transversal and to the parallel lines. So an example would be this one here and this one here. Those are, because they're in the same position, we say they're in a corresponding position. They are called corresponding angles. Okay, so corresponding angles are also equal. So they're the ones that are in a corresponding position. And again, that's the exact phrase you must use if you want to make sure that you get the marks in a question. And then the last thing that we have with parallel lines, and I'm just going to draw myself an extra set of parallel lines here just to sort of make this point, is that the two angles inside, on the interior of these pair of parallel lines, they total 180 degrees. So interior angles total 180 degrees. Okay, and sometimes, very occasionally, you hear them called co-interior angles, but I tend to use the word interior, and I think the textbook does as well. So interior angles total 180 degrees. Yeah, so if you were to think about a parallelogram, here's a parallelogram. So my parallelogram's got two pairs of parallel lines, one there and one there. We know that in a parallelogram then, we have effectively got this co-interior angles, these interior angles totaling 180 degrees there. and we've also got them totaling 180 degrees there. Yeah, so parallelogram is a very special shape. It's got a lot going on. If I just extend these lines as well on this parallelogram, we can also see, because we've got lots of things going on, that if I just take away some of these corners for the moment, this angle here and this angle here are going to be the same. That's because they are opposite each other. So that one there and that one there is going to be the same. This angle here and this angle here are going to be the same because they are corresponding, but they're also alternate with that one. That one there's the same, that's corresponding to that one over there, and alternate to that one there, and that one there have the same relationship. So in a parallelogram, we've got a lot of the relationships that we've talked about up here going on. So these opposite angles things, the interior angles, and we've got the corresponding, or that one in there, and those two would be corresponding angles. And we've also got the alternate angles going on. So lots going on. Okay, so that's the first bit. So corresponding, alternate and interior angles. Use them in questions when you are describing how you know that a certain angle is what it is. Okay, other things that are in this chapter. So this chapter is all about angles. So let's just think about a few more sort of things that it covers. One of the things that it has got in it is bearings. Okay, so bearings, we could just do a little note on. So bearings are always measured from the north. Key thing, so measured from the north. So if you have got 2 points, let's call them point A and point B, and you want to know the bearing of B from A, you always put your north at the one that you are going from. Okay, so measured from the north, from the point you start at. I should have said your starting point, but never mind, you start at. Yeah, and then your angle, if you are finding the bearing of B from A, your angle is going to be measured clockwise. Okay, so it's always measured clockwise. So it's from north, always measured clockwise. I'll write clockwise there. So in that direction. And then the last thing is that it is always given as 3 digits. So even if it was a 2-digit angle, so 90 degrees or something, you must write it as 0, 90. Yeah, e.g. I'll put that 0, 90 degrees. Yeah, not 90 degrees. So those 3 things must always be mentioned. Yeah, so always give all 3. Now the reason that it's in this chapter, all 3 points, the reason that it's in this chapter is that actually there is a relationship between bearings questions and parallel lines questions. And I'm going to just sort of extend this example here. So let's just say this angle, what does it look like? It probably looks like about 120 degrees, doesn't it? Should we say that's 120 degrees, 3 digits? So I could say here, bearing of B from A is 120 degrees. 3 digits measured from north in a clockwise direction. Okay, actually I shouldn't say give all 3 points, always use all 3 points would be a better thing to say. Right, now what about if we wanted the bearing of A from B? So if we want the bearing of A from B, we would draw a north, probably should put an N on there, we would draw a north from B. Now the important thing here to note is that your norths are parallel to each other. Okay, so I'm going to write when finding bearing of A from B, note that the norths are parallel. And if they're parallel, then we can use our knowledge of angles in parallel lines. Here we've got a transversal line, and here we've got two norths that are parallel to each other. This angle here and this angle here are therefore interior angles, which means that they add up to 180 degrees. If they add up to 180 degrees, B must be 180 minus 120, so this angle at B here must be 60 degrees. Yeah? So I'm going to write here, use interior angles to show, and I'll do my 180 minus 120 equals 60 degrees. And then the angle that I'm actually going to be interested in, remember my bearing has got to go from the north measured clockwise. My actual bearing is that one there. Yeah? So my actual bearing is going to be a full turn, 360 degrees, minus that 60 degrees, so it's going to be 300 degrees. So my actual bearing is 360 degrees minus 60 degrees, which is 300 degrees. Yeah? With bearings, my hint will always be draw a diagram. I don't think you can do these questions without drawing a diagram, to be honest. So I think you need to make sure that you draw a diagram and you put all the angles you know on it and put norths on it, and then you'll be fine. Okay, right, so that's bearings. So that's another angles thing. So if you need to take any notes on that, you take a note, and I'm going to write it out. Okay. Other things that we've got on the angles chapter. So there's a little bit about triangles, and I think probably you all know your definitions of your different types of triangle. So if you see a triangle that is marked up like this, that means that all the side lengths are equal. If all the side lengths are equal, it's equilateral triangle, and an equilateral triangle will therefore have equal angles. All the angles are 60 degrees. Okay. If you see a triangle that is marked up like this, that means it's an isosceles triangle. Two sides are the same length, and that means that the angles at the ends of those sides, not where they meet, but at the ends where they meet the other side, are going to be equal. So that one there is going to be X, and that one's going to be X. Yeah, that's a nice isosceles triangle. Try to learn how to spell isosceles. It will impress the examiner. I sit on Salisbury Cathedral eating lovely egg sandwiches is my personal way of remembering that. Okay, so those are a couple of triangles that you do need to recognise. Something else about triangles that it's worth remembering. You'll probably work it out as you go through a question, but it is probably worth knowing. So if you've got an angle A, an angle B, and an angle C on a triangle, remember that the A plus B plus C is going to equal 180 degrees always for a triangle. The angle on a straight line, though, we know is also 180 degrees. So this angle here must equal those two angles added together. That's always worth remembering. It's a bit of a quick way to get to an answer. because you know that A plus B plus C equals 180 degrees. This angle here has got a name. We'll talk about them in a moment in a bit more detail, but that's called the exterior angle of this triangle. Yeah, because it's not on the interior, it's on the exterior. It's the exterior angle. Other shapes that you need to know a little bit about, quadrilaterals. So quadrilaterals, they're the ones that have a total, quadrilaterals have an angle sum of 360 degrees. We've already talked about a parallelogram on a previous page. If you ended up with a shape that looks a bit like a parallelogram, like this one here, but you're told that all the side lengths are the same, that's a rhombus. Yeah, so it has two pairs of parallel lines. So which ones are parallel? Well, this one and that one are parallel, and that one there and that one there are they're both parallel lines, okay? But also all side lengths are the same. So that's what makes a rhombus rather than just a parallelogram, okay? The other thing about a rhombus is that the diagonals go from one vertex, one corner to another. The diagonals meet at 90 degrees, and they're the same length as each other. So that one is the same length as that, and that one's the same length as that. I should probably put a 3 there, and a 3 there. Okay, so something about the angles in a rhombus. Basically, the angles are going to be work in the same way as they do for a parallelogram. So this angle here is the same as that angle there. Opposite angles are the same. And that angle there is going to be the same as that angle there. And all the rules of parallel lines will also fit with a rhombus. Okay, and then the last shape that I just want to mention today that is also a quadrilateral is this shape here. It's called a kite. So a kite doesn't have any parallel lines. I'll just underline rhombus there. Kite doesn't have any parallel lines, but it does have some lines of the same length. That one and that one are the same length. That one and that one are the same length. Yeah, so it's got two pairs of equal sides. Equal length sides. It's got one pair of angles that are the same. One pair of equal angles, but not two. So that one and that one are not the same. What else about it? Oh yeah, and also, just like you would draw a kite in a picture book, its diagonals meet at 90 degrees. Yeah, so both of these are quadrilaterals, so all of their interior angles, all of those angles around the edges add up to 360 degrees. That goes without saying. And then you've got some other things going on. Now with both of these, if you sort of have a look at them, you probably see it more clearly on this one because I haven't drawn as much on it. You've actually got an isosceles triangle in the top part of that kite and in the bottom part of that kite. Same with the rhombus, that works in the same way. And you've got quite a few right-angled triangles going on as well. Yeah, so lots to pick up on these shapes. Be careful when you see those words in a question, because if they give you those words, kite or rhombus, they expect you to know about the shape. The last shape that I'm just going to draw down at the bottom here, I'm going to try and make it not look quite as much like a roof of a house. This one is a trapezium. The only thing that you need to know about a trapezium, it is a four-sided shape. It has one pair of parallel lines. And as long as you've got something with one pair of parallel lines, it's a trapezium. Yeah, it doesn't have to have anything else. This one looks like it's got some right angles there, but it doesn't have to have right angles there. It could look a bit more like the roof of a house. Yeah, or even that line could even come a little bit in that way. That would still be a trapezium. Yeah. So the only definition of a trapezium, other than it's got 4 sides and 360 degrees like any other quadrilateral, is that it has 1 pair of parallel lines. Okay, so that's all our sort of shapey stuff from this chapter. Last things I just want to talk about are congruent shapes and similar shapes, and then we'll just look at some polygons. Okay, so I'm rubbing this off. So, congruent shapes. Congruent shapes are exactly the same as each other. I'd say are exactly the same as each other. And that means if you cut one out and cut the other one out and put one on top of the other, even if you have to rotate it or flip it over, they would be the same. And that's because they've got same side lengths and the same angles. Yeah, and that's a definition of congruent shapes. Now, in maths, we do get a bit excited about congruent triangles. We talk quite a lot about congruent triangles. And congruent triangles are interesting because once you've got them with all the same side lengths, they absolutely have to have the same angles, okay? So, you can say that 2 triangles are congruent if all their side lengths are the same. And that's because no matter how you arrange those 3 sides, they've got to end up, when you cut them out, as being the same as each other. Look at that, that looks exactly like an equilateral triangle. I don't really want it to look like an equilateral triangle. And make it look a bit more like that. There we go. So, so a definition of an congruent triangles is 2 triangles will be congruent if their sides are all the same. Side, 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 if their sides are all the same. Yeah. Now, you might not be given information about sides and things on a triangle. So let me just say here, let's just do this in X, Y, Z. So those are my sides. So I would say on this one, A is equal to X, Y is equal to B. It would be nice if I'd written that the other way around, never mind. And C is equal to Z. That's how you would prove it, okay? The other ways of showing that triangles are congruent are if you can show that the side angle side rule applies, okay? So I'm going to say side angle side. Now that means we've got 2 triangles, try and make them look a bit the same. That means that this angle must be in the middle of the 2 sides, yeah? So if I've got an angle of, I don't know, 30 degrees, a side length of 5 and a side length of 3, 5, 3 and 30 degrees, then there is only one possibility for that final side, so they must be congruent. So what you would need to say for these triangles, X, Y, Z, if you were proving that these two triangles are congruent to each other, you would say AB, that side length there, equals XY, equals 5. You must say that. So you've ticked off your first condition, you've said side. The angle ABC equals angle XYZ equals 30 degrees. You've ticked off your angle, and then you could say for the last side, angle side BC equals side YZ equals 3. So you've satisfied your 3 conditions. You don't get the full marks on a question. If you are showing that these 2 triangles are congruent to each other, you don't get the full marks and that until you say, therefore, triangle ABC is congruent to triangle XYZ. Okay, you won't get the marks. Similarly on this one, with the side, 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 you would say, therefore, the triangles are congruent. So, sure those of you who remember this are thinking there are some other conditions as well. There are. So we've got side, 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 angle, side, where that angle is squeezed in between the 2 sides. There are 2 other conditions. One is angle, side, angle. So that's where the side that you're looking at has to be between 2 particular angles. So if I've got a 30 degree there and an 80 degree there, and that side length there is 3, you've got to have another triangle with a similar thing going on between an 80 degree angle and a 30 degree angle and a 3. You must show each thing individually, that angle is the same as that angle. Then you must say that side is the same as that side. Then you must say that angle is the same as that angle. Yeah? Angle, side, angle. And then at the end you must say, therefore, they are congruent. And the last one is if you've got a right angled triangle, the condition is that they've both got a right angle, their hypotenuse is the same, and one of the other sides is the same. And again, you must state each thing. Angle at vertex B is a right angle, and it's the same at vertex X, say. The hypotenuse of the triangle, the first triangle, is the same as the hypotenuse of the second triangle, equals 10 centimetres, say. And another side is 5 centimetres for both triangle A and triangle B. Therefore, they are congruent. You must show each of the conditions just the same way that I've done it here, and then you must state that they are congruent. So that's congruent triangles for you, okay? You must learn the conditions, yeah? And you must state each one as you're going through the question for your pair of triangles that you're looking at, and then you must say at the end, therefore the triangles are congruent, yeah? Each of the conditions, say it's congruent. Each of the conditions, say it's congruent. Okay, I think I've probably drummed that point into you. Okay, so we said shapes can be congruent. Congruent triangles have these very special conditions, and we get very interested in those in maths because triangles are special in that way. The other condition about sort of shapes that we look at are similar shapes. Okay, now with similar shapes, what we are looking at is shapes that have the same angles but are not the same size. So similar shapes, so they have the same angles. So if it was a triangle, it would be angle, 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 yeah, but not the same size. And therefore, one is an enlargement of another. And just like with the congruent shapes, where you have to show that one is congruent to another, with similar shapes, you do the same. You have the same idea, that you will show that one shape is similar to another. Okay, so I've got some triangles here, and can you see I've got a big triangle here and a smaller triangle here. I'm going to say that side length there is 6. I'm going to say that side length there is 9. I'm going to say that side length there is 4. and I'm going to say, what is this side length? Just this one here. Okay, the other thing I'm going to be told is that this line here and this line here are parallel to each other. So first of all, I want to show that these are similar shapes, okay? So these are similar shapes, and I'm going to have to name them, aren't I? A, B, C, call that D and E. So these are similar triangles because angle A, at the angle at A here, this angle here, is in both of the triangles, isn't it? So we're just going to say that it's shared between them. So angle CAB equals angle EAD. It's shared. I can say that this angle here, I don't know it's a right angle. It does look a bit like a right angle, doesn't it? But I don't know that for sure. So that angle there and that angle there, because these are parallel lines, and this is a line that is cutting across them, I can say that they are the same. So it's angle ADE. Remember, it's always the letter in the middle. Angle ADE and angle ABC. They are the same because they are, now let's think what the word is. So this one and this one, these are the parallel lines. That's the line that cuts across them. Let's just think about our parallel lines. So we've effectively got this angle here and this angle there. What are they called? They are called corresponding. Corresponding angles. And then finally, this angle here and this angle here, the same. So I can say angle AED, that one, and angle ACB are the same, again, because they are corresponding angles. Okay, so they are similar triangles. If they are similar triangles, that means that we can find the scale factor of enlargement between them. And we can find the scale factor enlargement because we've got corresponding sides here. This side here and this side here are corresponding. So our scale factor of enlargement is 6/4. Yeah, 6/4 is 1.5. We could leave that, or 3/2. I'll call it 1.5. Shall I? 1.5. So that's our scale factor of enlargement. It's saying, what do I have to multiply this side by to get it to be this bigger number 6? I have to multiply it by 1.5. Yeah. Okay, so that's going from there to there. Yeah. Now this side here, I know is 9. Actually, I'm not going to find x there. Sorry, gents. I'm just going to change this. I'm going to make this side here x. X is the one I'm going to find. So to find x, to find side length x, I'm going to use the corresponding side, which is 9 there. Now, if I multiply it by my scale factor of 1.5, I'm going to end up with a bigger number. I know that my x is a smaller number. So when I'm multiplying the smaller numbers up to get the bigger shape, I multiply by 1.5. If I'm taking the bigger numbers and I want to get them down to the smaller numbers in the smaller triangles, I'm going to divide by 1.5. Okay, so multiplying the 4 by 1.5 gets me to the 6. If I divide the 6 by 1.5, I get to the 4. The same will happen here. If I multiply my x by 1.5, I get to the 9. So to get back to the x from the 9, I divide by 1.5. So I can say, I'll say 1.5 times x is 9. So 9 divided by 1.5 is x. So x is going to be 6 centimetres. So this scale factor is an important thing. You need to look for 2 corresponding sides on your shape, and you need to divide one by the other. If you end up with a number that's bigger than 1, then you have got the scale factor that goes from small numbers to big numbers, the smaller shape to the bigger shape. If you do it the other way around, if you did 4 divided by 6, you would get 2/3, or 0.666666666, and that is what you would multiply the big number by to get to the small number. But the simpler thing to do is just to divide. Yeah, divide by 1.5. So find your scale factor of enlargement. If it's more than 1, you multiply by it to get to the bigger numbers. If you've got a number that's less than 1, that's the one that you're going to multiply by to get to the smaller numbers. Yeah, it's all about being bigger or smaller than 1. Okay, so multiply to get bigger, divide to get smaller for this number because it's a bit bigger than 1. Okay, right, so that's the idea of similar shapes and scale factors. Just want to mention one thing. We are looking here at scale factors that apply to side lengths. They're called linear scale factors, yeah? Just something to bear in mind that we did cover when we were doing this before. So if I've got 2 similar rectangles here, let's say, and let's say this one has got a side length of 3 here, and this one has got, just going like this, and this one has got a side length of, let's say 9. We know that our scale factor going from our 3 to our 9, it's going to be 9 over 3, which is 3, isn't it? We multiply by 3 to get that side length, yeah? Therefore, if this had another side length of 2, we know that if these are similar shapes, then this side length here, x, would be 2 times 3, which would be 6, yeah? Equals 6. So that's what using our scale factor to find our side lengths. Now, our area also is getting bigger, isn't it? Going from this shape to this shape. The question is the area getting bigger by a factor of 3? Let's have a think. The area of this shape, that's got to be 2 times 3, hasn't it? So it's got to be 6 units squared. Let's make them centimetres, and then we can make it all centimetres squared. Over here, my area, that's got to be 9 times 6, which is 54 centimetres squared. So going from 6 to 54, that isn't a scale factor of 3, is it? Our area scale factor here is actually going to be 54 divided by 6, which is 9. The relationship between the scale factor, or the linear scale factor, I'll call it, just for the lines down the sides, and the area scale factor is that the area scale factor is the linear scale factor squared. And that's always the case, regardless of the numbers, okay? So let's say, and you can make a note of this, for linear scale factor equaling k, your area scale factor will always equal k squared. Okay, so that's just a reminder of that. Last thing that I want to talk about for this chapter on angles is polygons and angles in polygons. Okay, so if you need to make a note of that, make a note of it. The last thing we're going to look at is polygons and angles in polygons. So I'm going to draw a polygon. Polygons are multi-sided shapes, okay? Angles in polygons. And the only one that I'm actually any good at drawing is a hexagon, so I'm going to draw a hexagon. And I'm going to use that to do my sort of my notation and things, okay? Now, these angles in here are called the interior angles, okay? So these are interior angles. They are sitting on the inside of your shape. And the sum of the interior angles for any polygon, sum of interior angles for any polygon is 180 multiplied by n minus 2, where n is the number of sides. So, need to know this, you need to remember this, okay? 100 times n minus 2, sort of makes sense. If you think about a three-sided shape, a triangle, 3 minus 2 is 1, 1 times 180, yeah, that's the sum of all the interior angles of a triangle. For a rectangle or any quadrilateral, you've got 4 sides, 4 minus 2 is 2, 2 times 180 is 360, and we know that the sum of the interior angles of a quadrilateral is 360. What this also, of course, does is it gives us the ability to work out the sum of the interior angles for any shape, however many sides it's got. So for this hexagon, 6 minus 2 is 4, 4 times 180 is 720. So for a hexagon, the sum of the interior angles is 180 times 6 minus 2, which is 180 times 4, which is 720 degrees. Now, if you've got a regular shape, for a regular shape, and remember, regular shapes, all sides are the same, all sides and all angles are the same. That means any interior angle, any single interior angle, is going to be your 180 times n minus 2 divided by the number of sides. So for my hexagon interior angle is going to be 720 degrees, this calculation on the top here, divided by my 6 sides, which means that any one of these angles is going to be 120 degrees if this was regular. So perhaps I ought to make it look regular, even if it doesn't look regular here, by saying all those side lengths are the same. Yep. Wouldn't be the case if it wasn't regular. We'd still have 720 degrees in total, but all the angles would be different. Now let's think about the exterior angles. Now the exterior angles on these shapes are these ones here. So it's where you extend the line that makes up the sides, and these would be our exterior angles. Now, our exterior angles, if I was to take all of these, whether they are all the same in a regular shape or not, the sum of the exterior angles is always 360 degrees. So in a regular shape, so for a regular shape, n-sided shape, I'll say, the exterior angle is 360 divided by n. So in this case, for our hexagon, so for a regular hexagon, it's going to be 360 over 6, which is 60 degrees. Now that also makes sense for another reason. Clearly, our interior angle and our exterior angle are lying on a straight line. So it must be the case, I'll write it up here and I'll write it in blue, that the interior angle plus the exterior angle equals 180 degrees. Now that's nice and that's very useful. The reason it's useful is quite often it's easier to find exterior angles than it is to find interior angles, or the maths is easier because you know your exterior angles all add up to 360 degrees in total. So interior angle plus your exterior angle equals 180 degrees. Very, very useful calculation. Okay, I think that's probably all that you need in terms of revision for polygons. In our Teams lesson on Thursday, we'll have a go at some questions on this. We'll do some similar triangles and congruent triangles questions, all of those slightly harder ones, and a few parallel lines questions. Okay, well done.